In this video, we're going to look at another method to reduce our execution path length, and that is having a 3-bus architecture. So previously what we had seen is we just had 2 full buses. We had our B bus, which loaded any of our registers or almost any of our registers into one of the ALU inputs, and then we had our C bus, which came from the output of our shifter ALU combo, and then loaded the result back into one of the registers. So what we're talking about doing now is, and let me maybe sketch this over here just for clarity. So we have our very poorly drawn ALU over here, right? So of course we'll have 2 inputs to that. So what we had before is we had some B bus coming in on this side. And so we said certain registers could be loaded onto our B bus, and our second input over here was always tied to our H register. So now what we're saying is let's add a full bus, and let's call this our A bus, and now we can feed into this from most of our registers. And we'll see a better drawing of this a little bit later on when we look at the second version, our MIC2 of our microarchitecture. And then of course we still have our C bus, which is on the output side, and that's storing the result back into any of those registers. And the main thing that this means in terms of our data path is that now we can add any 2 registers in a single cycle without having to use that H register sort of as a temporary holding register. So to look at specifics of that, let's consider our iLoad instruction sequence. And so that's shown down here below. And so again, this initial code is for if we only have a single ALU input bus, so we only have that P bus. So this is exactly the same as what we've seen before. Well, I say that not exactly the same. The one change is we do have this main 1 merged the same way as what we discussed in the previous video. So we've merged this main 1 with all of our microcode sequences, and really we're only going to see improvement when we have dead cycles. In this case, we did not have a dead cycle, so there's no change. It doesn't make it better. It also doesn't make it worse because we would have had to go to main 1 after iLoad 5 anyway. So what we can see though is in iLoad 1, well, maybe let's take a step back. So recall in iLoad, what we have to do is we have to identify a local variable. We then have to use some index operand to figure out where that variable is related to LV, and then we can find that, read that in. So what we see in iLoad 1 is we are setting our H to LV because we know we're going to have to add the index to our LV. And then in the next step, we're adding that index, which has been fetched as part of the previous main 1, and we're adding that to H, which is now holding LV. So it sort of takes 2 steps here, iLoad 1 and iLoad 2, to do what we're trying to accomplish, which is basically just LV plus our index, which is going to be in that MBRU. And again, MBRU, remember, is the unsigned version of our MBR. So we can clean that up a little bit if we have another bus. So if we have an A bus, what that now looks like, so this sequence down here is if we have an A bus and a B bus, is now we can combine that iLoad 1 and iLoad 2 into a single instruction, which is iLoad 1 in this new sequence. And so what we see here, highlighted in purple, is we can add these 2 registers directly. So we can just say MBRU plus LV, no need to use that holding register. We've only used 1 cycle of our data path. We go ahead and initiate that read as well. Everything else from there is pretty much the same. We're still having to increment our stack pointer. We're still incrementing our PC, fetching, writing, updating our 2S register, all of that stuff. And now we've got our main 1 sort of just changed to be iLoad 5, but we're still doing our PC equals PC plus 1, fetch, go to MBR, the same stuff that we've seen previously for our main 1. And so in this case, we're able to reduce our instruction sequence from up here we had, let's see, 6 counting our main 1, and down here we only have 5 counting our main 1. So again, we get some small, relatively small increase in speed, but if we're using this iLoad instruction over and over again, the more commonly used the instruction is, the more we're going to see benefits of the speed increase. Of course, there are several other instructions that would be able to be sped up by adding this A bus. I've not listed them here, but you could go and look through that figure on pages 272 to 274 in the textbook, and you could identify where several of those are. But we need to keep in mind that this comes at a cost, right? So we're not only having to add this extra bus, this A bus, we're also having to add control signals for any registers that is going on that A bus. So the same way we had to have a control signal to tell something whether we load it onto the B bus, we now have to have a control signal for everything that potentially goes onto the A bus. So this is our trade-off, right? So we can make this thing faster, but we have to have more hardware there, we have to have more area in our silicon die, which ultimately is going to translate to more cost.